You plug your phone in at night, you expect one simple story, electricity goes in, and the battery fills up, like pouring water into a cup. But you've noticed the awkward details. Sometimes the phone gets warm, sometimes the charger brick gets warm, sometimes nothing feels warm, yet the battery still rises, and sometimes the battery barely moves, even though you've left it connected for hours. So you do what people naturally do. You picture energy as a substance, a kind of invisible fuel. It travels from the wall through the cable into the phone. If the battery doesn't fill, you assume the energy must be lost. But lost where? Not where did the money go? Lost. Where the numbers still add up in some hidden account. You mean truly gone, as if something you had simply vanished. And that's the part that should bother you. Because in everyday life, disappearing is not a normal ending for a physical process. Spilled water doesn't disappear, it spreads out. A drop ball doesn't lose its motion, it turns that motion into other kinds of motion in the room. Even heat doesn't vanish. It drifts and mixes until you stop noticing it. Yet we casually talk as if energy can just disappear. We say it's used up. We say it's wasted. We say it's gone. And if you take those phrases literally, you walk away with a mental picture that cannot be right. So here's the precise question this video will answer. When energy seems to disappear, when a moving thing stops, when a battery drains, when a hot object cools, what is actually happening, step by step, that makes it look like the energy is gone? Energy doesn't vanish, it stops being useful. You probably carry a quiet assumption with you. When something stops, its energy is gone. A rolling ball slows down and comes to rest. A battery drains. A moving fan winds down. In each case, the visible activity ends, and it feels natural to say the energy has been used up. Let's examine that intuition carefully. Imagine a solid ball rolling across a wooden floor. At first it moves smoothly, then slowly it loses speed. Eventually it stops. Nothing obvious replaces the motion. The room looks the same as before, so the most tempting conclusion is that the energy simply vanished. But that conclusion creates a problem, because if energy could just disappear, physics would be unpredictable in a very deep way. You could never fully account for what happened in a process. Effects would have causes that partially evaporated. That is not how physical explanations work. So instead, physics starts from a stricter rule. Energy is conserved. It does not vanish. It does not get destroyed. It only changes form or location. The challenge, then, is not whether the energy still exists. The challenge is why you can no longer use it. Return to the rolling ball. As it moves, it rubs against the floor and the air. These contacts are not gentle. On a microscopic level, the surface of the ball and the surface of the floor are uneven. As the ball rolls, tiny bumps collide, bend, and snap back. Air molecules strike the ball and bounce away. Each of those interactions transfers a small amount of the ball's organized motion into microscopic motion in the surrounding matter. Nothing dramatic happens. No sparks, no visible vibration. But the energy is being shared, bit by bit, with the floor and the air. By the time the ball stops, that energy is still present. It now lives a slightly faster motion of countless atoms in the room. The temperature of the room has increased by an amount far too small for you to notice. So the energy didn't disappear, it spread out. This distinction matters. Energy that is concentrated, like the motion of a rolling ball, can easily be redirected. You can attach gears. You can lift weights. You can do work in a very specific way. Energy that is spread thinly, like a tiny increase in the random motion of trillions of atoms, still exists, but it has lost its usefulness at the human scale. A helpful way to think about this is not in terms of amount, but in terms of organization. The rolling ball had energy arranged in a simple, coordinated pattern. After it stops, the same total energy is present, but arranged in an astronomically complex and disorganized way. Physics does not say energy is destroyed. It says energy becomes harder to gather back into a form that does something obvious. And that shift from organized to dispersed is what your intuition mistakenly labels as disappearing. Stopping means sharing motion with the environment. When an object slows down, it feels natural to blame friction as a kind of eraser. You slide a book across a table. It moves, then stops. The motion is gone. So it's tempting to say friction destroyed it. But that picture hides the real mechanism. Let's slow the scene down in your mind. The bottom of the book is not perfectly smooth, and neither is the surface of the table. On a microscopic scale, both are covered in tiny hills and valleys. As the book slides, these surface features press, scrape, and collide with one another. Each collision does something very specific. A small part of the book's organized motion is transferred into motion of atoms in the table and the book itself. Atoms vibrate more strongly. Bonds stretch and relax. The table bends by unimaginably small amounts and springs back. This is not destruction, it is redistribution. To see why motion must slow as this sharing happens, imagine a single runner entering a crowded room. At first, the runner moves freely, but as they bump into others, some of their forward motion is transferred. Soon, many people are moving slightly in many directions. The original runner slows, even though total motion in the room has increased. Friction works the same way, but at a scale where you cannot track individual participants. The book stops not because motion is erased, but because its motion has been divided among so many microscopic degrees of freedom that no single object continues moving in a visible way. There is another important detail hiding here. Once motion is shared among trillions of atoms, it does not naturally recombine. The atoms move randomly. Their motions cancel out in every direction. There is no coordinated push to get the book sliding again. This is why friction feels one way. Not because physics forbids motion from returning, but because the precise coordination required is overwhelmingly unlikely. Every microscopic collision would have to reverse in just the right way at the same time. In practice, that never happens. So friction does not destroy energy. It converts organized motion into disorganized motion by coupling an object to its environment. When something stops, it hasn't lost its energy. It has donated it, quietly, diffusely, and irreversibly for all practical purposes, to everything around it. That is the physical reason stopping feels final, even though nothing has vanished. Heat is not a thing. It's motion you can't organize. By now, you might be tempted to say, fine, the energy turns into heat. That sounds reasonable, but it hides another misleading picture. In everyday language, heat sounds like a substance, as if friction creates heat and pours it into objects, the way water fills a container. That picture feels intuitive, but it's not how physics understands what's happening. So let's correct it carefully. Heat is not a thing that objects contain. Heat is a process. It's a name we give to energy while it is moving from one place to another because of a temperature difference. What objects actually have is thermal energy, the energy associated with microscopic motion inside matter. And that microscopic motion is the key. Return again to the sliding book. When its motion is shared with the table, the atoms in both objects begin to vibrate more intensely. They jiggle, stretch their bonds, and collide with neighboring atoms more often. None of this motion is coordinated. Each atom moves in its own direction, at its own moment, largely independent of the others. From far away, all of these tiny motions cancel out. You don't see anything moving, but at the microscopic level, there is more activity than before. That increased microscopic motion is what we mean by a higher temperature. So when we say energy turns into heat, what we really mean is this. Energy that was once organized into a single visible motion has become distributed among countless invisible motions that point in no preferred direction. An analogy can help here if we keep it on a short leash. Imagine a marching band moving down a street. Every step is synchronized. The motion is obvious. You could redirect it, stop it, turn it around. Now imagine the band breaks formation and everyone walks randomly through a park. The total amount of walking hasn't vanished, but there is no longer a collective motion you can easily use. Thermal motion is like that second scene. The energy is still there, but it has lost coordination. This is why heat feels fundamentally different from motion or electricity or lifting something against gravity. Those forms of energy are concentrated and directional. Thermal energy is diffuse and directionless. And this difference explains something subtle but important. You can easily turn organized energy into thermal energy. Friction does it automatically, but turning thermal energy back into organized motion is difficult and limited. You need a temperature difference. You need structure. And even then, only part of that energy can be recovered. Nothing in this process violates conservation. No energy disappears. What changes is the quality of the energy, specifically how organized it is at the scale you care about. And once energy reaches this disorganized state, it becomes invisible to your everyday intuition, even though it is still fully present. Why energy spreads out and doesn't come back? At this point, a reasonable question remains. If energy is conserved, and if nothing forbids motion from reorganizing itself in principle, then why does energy always seem to spread out and stay spread out? Why don't warm rooms spontaneously concentrate their heat into a single corner? Why doesn't the table ever give its energy back and send the book sliding again? The answer is not a hidden force or a preference built into matter. It's a matter of numbers. Consider a simple scene. You shuffle a deck of cards. There are an enormous number of possible shuffled arrangements. Now think about one very special arrangement, the deck perfectly ordered by suit and rank. Nothing in the laws of card shuffling forbids that ordered state. But if you shuffle randomly, you will essentially never get it, not because it's impossible, because it's outnumbered. The same logic applies to energy at the microscopic level. When energy is organized, like the motion of a sliding book, it corresponds to a very specific arrangement of microscopic motions. Most of the atom's movements are correlated in a way that produces a clear, visible effect. When energy spreads into thermal motion, the number of possible arrangements explodes. There are unimaginably many ways for trillions of atoms to share energy randomly, and only a tiny fraction of ways for them to line up and push in the same direction again. Physics gives this imbalance a name: entropy. Entropy is not disorder in a vague sense. It is a measure of how many microscopic arrangements correspond to the same large-scale situation. A warm, still room has high entropy because there are countless microscopic ways for its atoms to jiggle while the room looks unchanged. A rolling book has lower entropy because only a narrow set of microscopic motions produces that coordinated sliding. The second law of thermodynamics states that in an isolated system, entropy tends to increase. This is not a command, it is a statistical fact. Energy spreads because spreading corresponds to vastly more possible microscopic states. Concentration would require an extraordinary coincidence of motions occurring at the same time. So when energy fails to come back, nothing is being blocked. It is simply lost in a sea of possibilities. That is why heat flows from hot objects to cold ones, but not the reverse. Why friction slows things down, but never speeds them up on its own. Why time seems to have a direction in everyday processes. The world doesn't forget where the energy went. It just doesn't keep it organized. Why wasted energy is still conserved energy. When people talk about inefficiency, they usually mean loss. A light bulb that gets warm, an engine that heats the air instead of turning the wheels, a phone charger that feels hot to the touch. We say the energy was wasted, and the word quietly suggests that something has slipped away, but nothing has gone missing. To see this clearly, consider a simple setup, a battery connected to a small electric motor. When the circuit is closed, the motor spins. It lifts a weight or turns a fan. That part feels efficient, useful, purposeful. But very quickly the motor warms up. The wires warm up, the surrounding air warms up. Eventually, when the battery is drained, everything is still and slightly warmer than before. From a bookkeeping point of view, the story is simple. The chemical energy in the battery has been converted into motion, sound, and thermal energy. Add them all up, and the total matches what you started with. So why does inefficiency feel like loss? Because usefulness is a human-centered criterion. The battery's energy began in a highly concentrated, flexible form. You could use it to power a motor, light a lamp, or run a computer. After the process finishes, the same energy exists mostly as a tiny increase in the random motion of atoms in the room. That energy can still, in principle, do work, but only under special conditions. You would need a colder environment to create a temperature difference. You would need a carefully designed engine, and even then, only a fraction of that energy could be converted back into organized motion. This is not a flaw in engineering. It is a consequence of entropy. Every real process increases the number of microscopic arrangements compatible with the final state. Once energy has spread into many degrees of freedom, recovering it requires filtering out a very specific subset of motions. Most of the energy is locked into patterns that don't cooperate. This is why no engine can be 100% efficient, not because engineers lack skill, but because the physical world has more ways to be messy than tidy. Calling energy wasted is therefore a shortcut. What it really means is the energy has ended up somewhere we can no longer conveniently use it for our original purpose. Physics does not judge that outcome as failure. It simply tracks where the energy goes, and it never goes nowhere. What energy disappearing really means. By now, the pattern should be clear. Energy never vanishes, but it reliably drifts from forms that are easy to use into forms that are hard to gather back. If you zoom out far enough, this trend has a name in cosmology and thermodynamics, the long-term increase of entropy. Sometimes this is described loosely as the universe running out of energy. That phrase is memorable, but it is wrong in a precise way. The universe is not losing energy. As far as we can tell, the total energy remains accounted for. What the universe is losing is concentration. Stars shine because their energy is intensely localized. Hot objects cool because their energy spreads into colder surroundings. Over very long times, those differences flatten out. Imagine a universe that has reached complete thermal balance. Every region is at the same temperature. No gradients remain. In such a universe, energy is still everywhere. Every particle still moves. Nothing has been erased. But nothing interesting can happen either. No engines can run because engines require a temperature difference. No structures can grow because growth requires directed energy flow. No processes can unfold that distinguish one direction of time from the other. This hypothetical state is sometimes called heat death, not because motion ceases, but because usefulness does. And that brings us back to the original confusion. When energy seems to disappear in everyday life, what you are really noticing is the loss of organization. The world transitions from a small number of coordinated motions to an enormous number of uncoordinated ones. Your intuition expects energy to behave like a fluid you can track by eye. Physics tells a quieter story. Energy is conserved perfectly, while its ability to do specific jobs fades as it spreads. Nothing mystical is happening. Nothing is being destroyed. The universe is simply very good at mixing. And once you see that, the disappearance of energy stops being strange and starts being inevitable.